Hi everyone. In this module, we learn the concept of fractional precipitation. It is in analytical chemistry, first semester's KSOU syllabus. In Unit 8, we deal the concept of fractional precipitation, precipitation from homogeneous solutions, particle size, crystal growth, colloidal state, aging and peptidization phenomena, ignition of precipitates. After this unit, the unit 9 is also continue. The electrochemical methods of analysis. In that electrochemical methods of analysis, conductometry, concept of electrical resistance, conductance, resistivity, conductivity, specific conductance, molar conductance, equivalent conductance, and effect of dilutions on them, and measurement of conductance. In this module, we discussed both the units like Unit 8 and Unit 9. Now we are going to discuss with the fractional precipitation. The fractional precipitations means, already know that gravimetric precipitations, previous units. A gravimetric precipitating agent should react with specifically or at least any selectivity with the analyte and give precipitates the enough particle size for retaining on filter paper, high purity, low solubility, that no significant loss of the analyte occurs during filtrations and washing. The unreactive with air or any stables known stoichiometric composition after it is dried or if necessary ignited specific reagents react with a single chemical species. The selective reagents react with a limited number of species. The definitions of fractional precipitation. The fractional precipitations means it is the technique. It is the technique of separating of two or more ions from a solutions by adding reactant that precipitates first is ion, one ion, then another ion. and so forth. The solubility of an insoluble salt can be manipulated by adding a species react with the cations or the anions. Cations or the anions. Once again, fractional precipitation is the techniques of separating two or more ions from a solution by adding a reactant that precipitates first one ion, then another ion, and so forth. The solubility of an insoluble salt can be manipulated by adding a species that react with either the cations or the anion. When a salt contains the conjugate base of weak acid. Conjugate base means it accepts H plus ions, that is called what? Conjugate base. The pH will affect the solubility of the salt. We will quantitatively explore the situation involving a generic salt like MX, where X is the conjugate base of a weak acid. Just you consider MX, it is a salt, it undergo dissociation, M plus plus X minus. As the acid concentration increases, X minus react with protonic acids like H3O plus, forming HX and reducing the X minus concentration. As a result, more MX involves increasing the solubility. Next, what are the implemented of this concept? Addition of non-solvent increases the X parameters and leads to phase separation into the soluble phases. The same effect is accomplished by preferential evaporation of the solvent in a solvent or non-solvent mixtures. The Argand's constant X usually increases with decrease in the temperature, leading to phase separation in systems having LCST behavior. An increase of temperature gives the same result. The pure liquids and mixtures of solvents and non-solvents can be used as a solvent. From this concept or topic or units, the other important concept is what are the advantages of this. It is a very simple equipment and easy handling. The precipitation, phase separation and isolation at constant temperature. The good control of precipitated mass of polymer via volume of precipitant when precipitation behavior of the system is known. What are the disadvantages of this method? the dilutions of the systems during proceeding fractionations due to addition of non-solvent. This results in a disadvantageous course of polymer concentrations. If it is difficult to obtain narrow fractions of a high molecular weight, increase in the fractionation volume with each fractionation step. One starts with a relatively small volume of the solution that contains only a small quantity of polymer. A gradient of precipitant concentrations occurs near the precipitant inlet. That despite these disadvantages, downwards precipitations, fractionations is the most used precipitation procedure. It may be considered as starting point for all other fractionation procedures. The particle size and filterability of precipitates. The particle size is one of the important criteria in that precipitates. The particle size of solids formed by precipitation varies enormously. At one extremes are colloidal suspensions, whose tiny particles are invisible to the naked eye. The colloidal particles show no tendency to settle from solutions and are difficult to filter. At the other extremes are particles with dimensions on the order of tenth of a millimeter or a greater. The temporary dispersions of such particles in the liquid phase is called a crystalline suspensions. The particles of the crystalline suspension tend to settle spontaneously and are easily filtered. Precipitates consisting of large particles are generally desirable for gravimetric work because these particles are easy to filter and wash free of impurities. What are the factors that determine the particle size of precipitates? Factors that determine the particle size of precipitate. Precipitate formation has been studied for many years, but the mechanism of the process is still not fully understood. What is certain, however, is that the particle size of the precipitate is influenced by precipitate solubility, temperature, reactant concentrations, and the rate at which reactants are mixed. The net effect of these variables can be accounted for at least quantitatively by assuming that the particle size is related to a single property of the systems called relative supersaturation. Here, relative supersaturation is equal to Q minus S by S. Q is the concentration of the solute at any instant. S is the concentrations of solute at equilibrium. A supersaturation is an unstable solution that contains a higher solute concentration than a saturated solution. As excess solute precipitates with the time, supersaturation decreases to zero. Generally, precipitation reactions are slow, so that even when a precipitating reagent is added drop by drop to a solution of an analyte, some supersaturation is likely. The experimental evidence indicates that the particle size of a precipitate varies inversely with the average relative supersaturation during the time when the reagent is being introduced. When Q minus S by S, that is what relative supersaturation is large, the precipitate tends to be colloidal. When Q minus S by S is small, a crystalline solid is more likely. The nucleation and particle growth. Nucleation means the initial formation process in which a minimum number of atoms, ions or molecules join together to give a stable solid. Often these nuclei form on the surface of suspended solid contaminants such as dust particles. The particle growth means the subsequent growth after nucleation. If nucleation predominates, a precipitate containing a large number of small particles results, and if growth predominates, a smaller number of larger particles is produced. What are the experimental control of particle size? A lower the relative supersaturation value, the larger particles. Increase supersaturation by heating to increase the solubility of pH adjustment. Adding complexing agent. Similarly, increase Q by using dilute precipitating solution, adding precipitating agent slowly and stirring using homogeneous precipitation technique. What are the colloidal particle precipitates? The individual colloidal particles are so small that they are not retained by ordinary filters. Moreover, you know that Brownian motion or Brownian movement prevents their settling out of the solution under the influence of gravity, because the particle size is movement in zigzag motion. Fortunately, however, we can coagulate or agglomerate the individual particles of most colloids to give a filterable amorphous mass that will settle out of the solution. When liquid starts to thicken and becomes solid, it coagulates. What is the coagulations of colloids? Coagulations can be hastened by heating, by stirring, and by adding an electrolyte to the medium. To understand the effectiveness of these measures, we need to look into why colloidal suspensions are stable and do not coagulate spontaneously. Colloidal suspensions are stable because all of these particles of the colloids are either positively or negatively charged and thus repel one another. The charge results from cations or anions that are bound to surface of the particles. We can show that Colloidal particles are charged by placing them between charged plates where some of the particles migrate towards one electrode while others move towards the other electrode of the opposite charge. The process by which ions are retained on the surface of a solid is known as adsorption. Anyhow, this is a very small topic. From this topic, we understanding the questions like that. Here, aluminium 3 plus from the solutions that contains Mc2 plus, nickel 2 plus from the solutions also contains U2 plus, and he explained why silver iodide co-precipitates silver acetate much more than silver chloride. Gelatinous precipitates are not digested, and chelating agents are generally insoluble in water but soluble in organic solvents. Some reasons are required. Okay, these are all expected questions, just to go through that. Next, we'll continue on that in electroanalytical techniques. This is Unit 9, electroanalytical techniques. From this Unit 9, that is electroanalytical techniques. In that, electroanalytical techniques include measurement of electrical properties such as current, resistance, and potential voltage, reciprocal of resistance, that is conductance, and evaluations of materials generated at the electrode. All the measurements are directly related to concentrations of analyte. A brief summary of various electroanalytical techniques classified according to quantity measured is given below. The electroanalytical techniques are classified as potentiometry and chronopotentiometry, voltometry and polarography, conductometry, oscillometry, amperometry, electro gravimetry, collometry, controlled potential separation. These are all the different types of or different classifications of electroanalytical techniques. The potentiometry, it is the direct applications of Nernst equation. It involves measurement of potentials of non-polarized electrodes under conditions of zero current. Chronopotentiometry, a known constant current is passed through the solution in potential appearing across the electrodes is observed as a function of time. The related measurement of current changes following applications of constant potential is known as chronoamperometry. The voltometry or polarography. The voltometry. In this method, the studying the composition of dilute electrolytic solutions by plotting current voltage curve is known as voltometry. When a dropping mercury electrode is used as cathode and mercury pool is used as anode, the technique is called the polarography. In that, the conductometry, in this analytical method, two identical inert electrodes are employed and the conductance between them is measured. The technique involving titrations is called the conductometric titrations. In this, archeometry, in this method permits one to observe change in conductance, dielectric constant or both by the use of high frequency alternating current. Electrodes are not kept in contact with the solutions directly. In amperometry means, it refers to the measurement of current under a constant applied voltage. Under these conditions, it is the concentrations of analyte which determines the magnitude of the current. In Electro Gravimetry, in this analysis, the elements to be determined is deposited electroanalytically upon a suitable electrode by the process of electrolysis. In colorimetry, in this method of analysis involves the applications of Faraday's law of electrolysis relating the equivalence between the quantity of electricity passed and the amount of substance generated at the corresponding electrodes. That controlled potential separation. It is possible to quantitatively separate species by means of electrolytic oxidation or reduction at an electrode. The potential of which is carefully controlled. The quantity of separated species may be measured colorimetrically or gravimetrically. Only three electroanalytical techniques such as Electro Gravimetry, colorimetry and polarography based on exhaustive electrolysis of analyte are discussed in next chapters. Exhaustive electrolysis means the analyte is quantitatively oxidized or reduced at the electrodes in an electrochemical cell. Before going to discuss the topics, it is throughout worthwhile to give a brief idea about the various electrical components involved in electroanalytical techniques. In that electrical components, the electrodes and electrode potential. The electrode is the system through which current enters or leaves the electrolytic solution. It may be metallic or membrane. Only metallic electrode relevant to the topic is discussed here. One is the electrode and electrodes of kind, the inert redox electrodes. Electrode of the first kind. It consists of pure metal. M is dipped in the solutions of its own ion, Mn+, like copper is dipped in that copper 2+, zinc is dipping in that Zn2+. The potential difference of potential is set up the interface. A single reaction such as involved and the electrode potential X is given by Nernst equation. We are going to take a simple example here. Zn. It liberates 2 electrons with standard oxidation potential. What is the value? Here 0.76 volt. That is equivalent to reduction of same thing. Zn is gaining of 2 electrons. What it becomes Zn? With standard reduction value is minus 0.76. The examples of such electrodes include silver, mercury and copper, zinc, cadmium, bismuth, titanium, lead, etc. These are all the examples. Electrodes of the second kind. It consists of pure metal, that is represented by M, coated with one of it sparingly soluble salt of the type MXN. In this electrode, the potential is a function of the concentrations of X minus in an MXN by M, that is Redox reaction. The Nernst equations of this here, Nernst equation, E is equal to E naught minus 2.303 nRT by log X. That is Nernst equation. What is the inert redox electrode? In that inert redox reduction, the electrode includes inert conductors like gold, platinum or palladium immersed in solutions containing redox systems. It is an inert electrode which serves as a source or sink for electrons for a redox reaction. For example, platinum electrode immersed in a solutions containing cerium 3 plus and cerium 4 plus ions in an examples of such electrodes. The reaction being involved is cerium 4 plus and the Nernst equation for this electrode. That electrochemical cell. In electrochemical cell, measurements are done in electrochemical cell. It consists of two electrodes, namely the cathode and anode, each of which is immersed in an electrolytic solution. However, in most of the cell, the solution surrounding the two electrodes are different and must be separated to avoid direct reactions between the reactant. This is done by inserting a salt bridge between the solution. The conductions of current from one electrolyte solutions to the other occurs by migrations of K plus ions in the bridge in one direction and Cl minus in the other direction. The electrochemical cell may be either galvanic or electrolytic as follows. We consider it is a galvanic cell. Galvanic cell means the chemical energy is converted into an electrical energy, that is galvanic cell. Here copper is there. Copper electrode dipping into copper sulfate solution. Silver electrode dipping into a silver nitrate solution. Both are connected externally through a wire along with voltmeter, internally through a salt bridge. Salt bridge means it is a solution of potassium chloride solution. Here copper, it liberates electron, it undergo oxidation. The copper, it liberates electron. Liberated electron is moving towards that silver. Liberated electrons moving towards that silver. That the potential value is based on that number of electrons. To increase the number of electrons, the potential value is also increases like that. Once these liberations of electrons, it undergo both oxidation and reduction, the chemical energy is converted into an electrical energy. Okay. In electrolytic cell, it is an electrochemical cell through which the current is forced to flow by supplying electrical energy from an external source. This results in electrolysis. In this cell, the cathode and anode are attached to negative and positive terminal of the external source. Generally, in an electrochemical cell, the potential of one of the electrode is sensitive to analyte concentration. It is called working or indicator electrode. The second electrode is called counter electrode, which serves to complete the electric circuit and provides a reference potential against which the working electrode's potential is measured. Ideally, the counter electrode potential remains constant so that any change in the overall cell potential is attributed to the working electrode. The most common reference electrode is what? Standard hydrogen electrode. The standard hydrogen electrode is constructed by using 1 molar hydrochloric acid. The platinum electrode is dipping into that 1 molar hydrochloric acid solution by passing pure hydrogen gas into that, maintain 1 atmospheric pressure. The platinum electrode is act as a hydrogen electrode. The electrode potential value of SHE is 0. That's why that is used as a reference electrode. That is used as a reference electrode. This is the electrical circuit. In that electrical circuit, that is generally used in electroanalytical techniques. This is batteries or cell. This is plug key. This is solutions, etc. In this circuit, a storage battery is what is connected across uniform resistance of wire. AB is along with the contact maker. D can be removed. The fall of potential between A and D can be varied gradually. A voltmeter V is placed between the two electrodes of the cell. To indicate the EMF, electromotive force, to the cell for electroanalysis. A milliliter M is placed in the circuit resistance in the circuit to indicate the magnitude and directions of any current in the cell, and S is the switch or key. The galvanostat and potentiostat. The modern electrochemical instruments provide automated electronic means of controlling and measuring current and potential. These include galvanostat and potentiostat. A galvanostat is a device used to control the current in an electrochemical cell, while potentiostat is the device used to control the potential in an electrochemical cell. That electro gravimetry. The electro gravimetry is an electroanalytical technique in which the amount of an analyte present in the sample in solution is found by determining the weight of the product of analyte deposited at the electrode during exhaustive electrolysis. In this method, generally the metal to be determined is quantitatively plated onto the platinum electrode, and from the weight gained by the cathode, the amount of the metal present in a sample is calculated. What is the theory and principle of electrogravimetry? The electrogravimetry is governed by Ohm's law. Faraday's two laws of electrolysis is discussed. This is Faraday's law for Ohm's law. What is the Ohm's law? This law expresses the relation between three fundamental quantities such as current, electromotive force and resistance. According to this law, the current I is directly proportional to the electromotive force X and inversely proportional to the resistance R. Your current is equal to X by R. Faraday's first law. The amount of different substances deposited or liberated at the electrode of a cell is directly proportional to the quantity of electricity passed through the solution. Mathematically, W is directly proportional to Q. Here W is equal to X into Q. Here W is the weight of the substance deposited at the electrode of the cell. X is the constant of proportionality called electrochemical equivalent of the substance, and Q is the quantity of electricity passed. That Faraday's second law, the amount of different substances which are deposited or liberated by passage of the same quantity of electricity are proportional to the chemical equivalence. Chemical equivalence is the calculated by dividing atomic weight by the number of electrons involved in the respective electrode process. Here, the weight of the copper deposited is equal to the chemical equivalent of copper. Here, both are equal. In that electro gravimetry calculations, let the weight of the sample containing the analyte be Ws gram. Suppose the analyte be a metal ion Mn plus. It will be plated onto a cathode as metal M due to the reduction during electrolysis of its aqueous solution. Mn plus Ne gives M. Let the weight of the properly cleaned and dried cathode be W1 gram before electrolysis. After the electrolysis, the cathode is removed from the solution, properly washed and dried. Let the weight of this plated cathode be W2 gram. Weight of the metal deposited at the cathode during exhaustive electrolysis is W2 minus W1 gram. Here Ws is the samples contains W2 minus W1 gram of analyte. The percent of analyte present in the sample is equal to W2 minus W1 by Ws into 100. What are the advantages of this electro gravimetry? No filtration is required. Co-deposition of the metals, that is, deposition of other metal ions along with the analyte, can be avoided by controlling the experimental condition. It is rapid, selective and equally sensitive. What are some important requirements for electrogravimetry? The deposit must adhere firmly to the electrode. The deposit must be quantitative. The deposit must be inert of the known composition. What are the different types of electrogravimetry? Electrolysis of a electrolytic solution is dependent on the number of factors such as the applied voltage, electrode potential of the working electrode, the current flowing in the cell, and the amount of electricity consumed during electrolysis. Smooth deposition is also affected if evaluations of a gas takes place simultaneously and if the current is too large. Therefore, by adjusting either the current or the voltage applied to the cell, the current and gas evaluations are controlled. On the basis of these factors, the electrogravimetry methods give rise to the following types of electrogravimetry: electrolysis in the simple cell, electrolysis at constant current, electrolysis at constant voltage, electrolysis at constant controlled potential, spontaneous or internal electrolysis, electrolysis at the anode. These are all. Electrolysis in simple cell. Electrogravimetry involving simple cells such as non-galvanic and galvanic cells is discussed below. Electrolysis in a galvanic cell. Electrolysis may be carried out in a simple cell which is non-galvanic. This type of cell consists of a pair of inert electrodes. dipped into the electrolytic solution. The two platinum electrodes inserted into an aqueous solutions of copper sulfate and electrical connections are made as shown figure. This is variable electrode, DC voltage source. This is platinum anode, this is the steering bar, platinum gauze cathode, this is the magnetic stirrer. As the two identical electrodes are placed in the same solution, they have some potential and there is no potential difference between them. So the cell is the galvanic cell. The concept of decomposition potential. Here the applied voltage is gradually increased by moving the contact maker. Virtually no current flows through this cell. However, when the applied voltage reaches a certain value, a noticeable reaction will be observed. For example, in the case of copper sulfate solution, the cathode becomes reddish brown due to deposition of copper and bubbles of oxygen gas around the anode are evolved, indicating electrolysis to make place. The electrolytic reactions being Cu2 plus 2E minus getting Cu, that is reduction at cathode. 2H2O gives O2 plus 4H plus 4E electrons, that is oxidations at anode. This is the graph of this current voltage curve for Electro Gravimetry. The explanations for decomposition potential, that back potential. During an electrogravimetric operation, a galvanic cell is built up from the product of electrolysis on the electrodes. If the current is switched off, the product tends to produce a current in the direction opposite to that passed during electrolysis. The voltage applied to the electrolysis cell must exceed that of galvanic cell, which is created during electrolysis. This is always in opposition to applied voltage and can be written as X back. Thus, if there is no other factors affecting electrolysis, the potential will be equal to the galvanic cell potential setup during electrolysis. Thus, during electrolysis of copper sulfate solution, deposition of copper in the electrode produces copper electrode and evaluations of oxygen at the anode produces oxygen electrode. Suppose for simplicity, the ions are at unity activity and the partial pressure of oxygen above the solution is 1 atmosphere. We can calculate the standard EMF or voltage of the cell from the values of standard reduction potential. In ohmic potential or IR drop, the electrochemical cells like metallic conductor resist the flow of current in accordance with Ohm's law. If X is the potential difference in volt across the cell, then according to Ohm's law, X is equal to IR. R is cell resistance, I is current passing through the cell. Here what is that external potential is equal to cell potential plus IR. The over potential or over voltage. The over voltage may occur anode as well as cathode. Due to this, the experimentally which is the nature of the electrode employed for the electrolysis, and in many instances higher than the calculated back potential. What are the causes of this overvoltage? The overvoltage arises due to concentration, polarization, and activation factors as discussed below. The concentration polarization. The concentration polarizations means if there is a change in concentrations or concentrations gradient exists in the immediate vicinity of the electrode, a new phenomena called concentration polarization. For example, in the electrolysis of acidic solutions of copper sulfate between two platinum electrodes, concentration change occurs near the vicinity of anode and cathode. At the cathode, depletions of copper ions occurs near the surface. As a result, the reversible potential of the copper electrode shifts in the negative direction. At the anode, accumulations of hydrogen ions and evaluations of oxygen gas cause the reversible potential of oxygen electrode to shift in the positive direction. The activation over potential. This arises due to slow kinetic step in the overall electrodes process and is particularly pronounced when a gas is liberated at the electrode. For example, in the reductions of H plus at the cathode, the initial electron transfer step yield hydrogen atoms. Here, hydrogen gaining of electron, it becomes H. To form the final product hydrogen gas, the atoms must combine. 2H gives H2. The another resistance of activation over potential is encountered during oxidations of water to form oxygen occurring at anode. The magnitude of this over potential depends on the chemical nature of electrode material and its physical state, the temperature, the rate at which the electrolysis is performed on current density. What are the expressions of total potential applied to cause electrolysis? Here this is the over potential. X potential is equal to X cathode plus X minus X anode minus S oxidations ion. This is the OC and OE are over potential at cathode and anode respectively. Here X is equal to X OC minus X OE. The over voltage due to evaluations of oxygen at anode is 0.4 volt. Thus, the applied potential required to carry out the electrolysis for deposition of copper from copper to solution. In electrolysis in a galvanic cell, the galvanic cell is also shown in the figure, can be made electrolytic cell by connecting the positive terminal of the battery having a potential somewhat greater than 0.412 volt to silver electrode and a negative terminal to the copper electrode as shown in the figure. An external voltage source is required for the conversions of galvanic cell to electrolytic cell. The arrows through the source means we can vary the external voltage but applied to the galvanic cell. If we apply a voltage greater than 0.412 volt, a current will flow but it will be in opposite direction. Electrons will flow from negative side of the external source into the copper electrode and they will flow away from the silver electrode to the external circuit. Here this is 2Ag gives C2 plus 2Ag plus C. The process is called Electro Dialysis, and this cell, which was Galvanic Cell earlier, is now an Electrolytic Cell. What is the electrolysis at constant current? The principle of this experiment. In this method, electrolysis is carried out at constant current. As the electrolysis occurs, the concentrations of the analyte steadily decreases. As a result, the current due to its oxidation and reductions steadily decreases. Hence, to maintain a constant current, the applied voltage is to be continually increased. However, the potential of the working electrode of the electrolytic cell cannot be controlled, and this technique is therefore known as Electro Gravimetry without potential control of the working electrode. With the experimental setup of this electrolysis at constant current. This is the experimental setup. The electrolytic cell. In the external circuit, it consists of DC power supply, a source of current, an ammeter and voltmeter to indicate the current and voltage respectively applied to the cell, a rheostat to adjust the applied voltage so that initial voltage reading in voltmeter is maintained till end of the electrolysis. A galvanostat may also be used to control the current, and this process is called Amperostatic Electrogravimetry. Is the working of this. The problems encountered in the electrolytic at constant current. In this technique, cathode potential is not controlled. During electrolysis, as the concentrations of analyte being deposited at cathode decreases, cathode potential also decreases. As a result, a new electrode process can occur. If this new process a deposition of a second metal, the selectivity of the analysis is too lost because the weight of the deposit does not represent a pure metal. If no other metal ion that can be deposited is present, then hydrogen gas is evolved by the reductions of water. Sometimes this may be helpful since the gas evaluations may improve mass transfer of the metal being deposited, thereby shortening analysis of time. However, if appreciable evaluations of hydrogen occurs, the deposited will easily broken up so that irregular spongy poor adherent deposits are obtained under such condition. These are all MCQ questions. No one will ask your MCQ questions in your examination. No fill in the blanks, no true or false. This is a very short answer type question. Just you go through that. And what is meant by working electrode, potentiostatic gravimetry, Faraday's law, Ohm's law, amperostat, and metal deposition. Short answer type question. Polarization, kinetic polarization, galvanostat, amperostat, reference electrode, counter electrode, and reasoning type questions, and long answer type questions. Okay, these are all very important to your examination. Okay, please go through that unit 8 and 9. Okay, thank you one and all.